Hello scientists, this is MsR and we're going to talk about Lab 7.09, sound waves. Here's a wave diagram just briefly to help you. Remember, the crest of the wave is the topmost part of the wave. The trough is the bottommost part of the wave. One wavelength is all the way to the top and all the way to the bottom and back to the middle. We're going to use fetcolorado.edu, this simulation called Sound. I'll show you what that looks like and how to download it. So if you click on the link in the lab, you'll get to this page and you'll have to click on the play or download, and then it should open, or if you're in a Mac, you might have to go to your downloads folder and right-click on it and then hit open. Don't worry if your computer gives you warnings. It's a very safe site. You can download all of the materials without concern for viruses. So when we get to the simulation, we need to figure out what is the effect of changing the frequency of the tone generated and the effect of changing the amplitude. So we're in the tab called Listen to a Single Source, and we're going to look at frequency and amplitude. We're going to want to make sure we're audio enabled here because we want to make sure that we can hear what's going on. So I'm going to hit the play button down here. You probably can't see it on your screen. And we're going to change the frequency. As the frequency goes up, the pitch changes. What we hear, pitch is how we hear frequency. As we decrease the frequency, the pitch gets lower. So remember, pitch is how we hear frequency. Now let's play around with amplitude. Let's turn the amplitude way up. Let's do it at a different frequency. Turn the amplitude way up. I'll do it again. So what effect does amplitude have on how we hear the sound? And what effect does frequency have on how we hear the sound? I hit the pause button at the bottom of the screen. Now let's go answer some questions. So we've looked at both 1 and 2 here, and I see it should be effect, because affect is the verb. So now let's look at number 3. Using the slide bar as a rough ruler and the frequency set to 100, how low in amplitude can you still hear the tone? So we're going to set it for a low frequency, which means a low pitch. We'll hear a low sound. And then we're going to see kind of what percent of the amplitude we can still hear the sound. We're going to do the same at 1,000 hertz, which is a much higher sound, a higher pitch. And we're going to see at what percent amplitude we can still hear the tone. So 100 and 1,000, we're going to see the differences. So we're going to set the frequency to 100 here. There we go. And I'm going to hit play down here. I'll scoot this up so you can see. I'll keep turning it up until we can hear it. I can't really hear it at all. Maybe we should set it a little bit higher. We'll set it at 200. We'll set it 156. We still hear it? Nope. So it looks like if we use the amplitude slider as kind of a percentage, and we assume this is 50%, and each of these ticks is 10%, let's see if that works out. 10, 20, 30, 40, 50, yep. So this is 50%, and each tick is 10%, so let's go down to 40, 30, maybe like just over 20% we can hear it. At the lowest frequency we can hear. 100 was a little too low. Now we need to repeat this at 1,000. So let's turn it up to a frequency of 1,000. We can still hear this. And now let's see how low we can go and still hear it. We can turn the amplitude down quite a bit, just about like, thought maybe 8% versus the 25% we needed for a lower sound. So it looks like, and it seems like, that higher sounds carry better. And when you think about it, if you want the noise of an ambulance or a police siren to carry, they're very high sounds. They're much more similar to the high frequency sound that we're hearing right now than the low frequency. A siren doesn't sound like this. And there's a reason a siren doesn't sound like this. We have 222 hertz turned all the way up. We have the amplitude as high as it will go, or the volume as high as it will go, and it's hard to hear. So it seems like if we turn up the pitch up, turn the hertz up, increase those hertz, we can hear it further away. So now you've got the information to answer 3 and 4. We know it's kind of hard to hear low pitch sounds, low frequency sounds. We needed to have the slider bar up to about 25% to hear anything. And we needed to have the slider bar, we could go down to like 5% here and still be able to hear 1,000 hertz or a high pitch. And that makes sense if you think about what pitch ambulances are. And I think you know enough at this point to answer number 5. Do you have better high-end or low-end response to your ears? Think about how babies cry. We have a vested interest as humans in being able to hear our young. They don't have really low cries. Babies don't go, they're pretty high-pitched. And that's something to think about as well when you answer question 5. So we're going to talk about constructive and destructive interference here. I will let you go and look at the definitions here, and we will watch constructive and destructive interference here. Here's the bite-size website that's in your handout, and I will let you pause the video and you can read all about constructive and destructive interference. So here's the second web address on your sheet under constructive and destructive interference, and you can see 2 waves interacting. Right now they're doing constructive interference because the added wave is getting bigger, and now they're having destructive interference because the added wave is getting smaller. Basically what is happening is waves are added to each other. And if one wave is high and one wave is low, let's see, this is +1 and this is -1, they add to 0. If they're both +2, then they add to +4. And you can see that happen right here. It's getting taller because they're both positive here. And as one's getting more up and the other one's getting more down, they go to 0 and then they start adding again. Or actually they pass through each other and then they're just done. As they pass through each other again, you can see wave 1 is low and wave 2 is low and wave 1 is high. Now they're both high and they're adding. Now they're kind of getting to 0, and they're back to the middle. So waves can either add up and get taller if they're both, if the troughs add. If one wave is a trough and one wave is a crest when they're adding, they add to 0 and they come to the middle. You can watch this a little bit more if you'd like. So now we should have enough information to answer questions 6 and 7. We've been to the Bite-Size website and read the definition, and we've watched constructive and destructive interference happen. So now we want to know what happens to the shape of the wave when two crests collide. Well, when they're in phase, they add, and constructive interference looks like this. You add these two waves. If this is +1 and this is +1, you get +2. What happens to the shape of a wave when a crest and trough collide? Well, if this is +1 and this is -1, you get 0. So I think you have enough information here to answer questions 6 and 7. Let's go to the next section. We need to open the panel in the simulation called two-source interference by clicking on the blue tab at the top. It'll look just like this. We want to make sure we have Enable Audio box checked, like we did in the last simulation. You'll hear differences better if the frequency is greater than 700 Hertz. So we'll have to make sure that we set the frequency to 700 or above. So we're going to look for light and dark bands on the sound, on the speaker, emanating from the speaker, and look at what those represent. We're going to move the head of the listener up and down by clicking and dragging. And what do we note about the locations where the waves intersect? And we're actually going to switch it so we can hear and like the listener is hearing. We can basically be the listener on the screen. And I'll show you what that means. So we're back in the simulation right now, and here we're going to click on two-source interference. We're going to click Audio Enabled. We're going to click 700 Hertz or better. We'll go to 800 here. And you can kind of hear there's a little woo, kind of a waver in the sound. Let's move this the ear of the listener. Do you see these patterns here? These kind of fuzzy patterns. There's kind of lines emanating from the speaker. If we put the listener's ear in one of those lines, here I'm moving to another one. You can hear the volume. Now I kind of put him in the sweet spot. The perceived volume is very different. I'll hit the pause here down below the screen. So we can see that the waves here are running into each other from these two different sound sources, and they're interfering with each other. And we just learned about constructive and destructive interference. Where it's louder, what do you think is happening? And where it's softer, what do you think is happening? So let's just for a moment think about sound in terms of constructive and destructive interference. We know that amplitude affects volume. So if we have a larger amplitude, we'll probably hear a louder sound. If we have a lower amplitude, we'll probably hear a softer sound. So you can think about what happens when sound waves collide, and if there's constructive and destructive interference based on how the listener hears the different sounds, or hears different volumes in different places between those speakers. So here's a question. It says, in the areas where the waves intersect, moving the head of the listener less than a centimeter on the screen changes the sound a great deal. Why? It gets louder and softer. Think about what you know about constructive and destructive interference and how amplitude, a big amplitude is a loud sound, and a low amplitude is a soft sound. When those waves are coming from two different speakers, they're going to interact constructively and destructively and create areas that have different degrees of amplitude and if they have different amplitudes, they're going to have different volumes. So there you also have the answer to question 11. There's changes in local pressure. Sound waves are colliding. They're colliding constructively and destructively. They have different amplitudes, and we hear those different amplitudes as volume. If you really want some more help, you can go to these websites on your lab sheet. All right, we're going to go to a different part of the lab now. We're going to open the simulation called Listen with Varying Air Pressure. It's going to be the last tab in the simulation. We're going to leave the pressure set to 1 atmosphere and adjust the amplitude of the sound at a fixed frequency. I think we don't know what we're supposed to do there. Well, let's see what happens. Then we're going to adjust the pressure down using the Remove Air from the Box button at the bottom of the slider box and record the relative loudness at 5 data points. Make up your own scale for loudness, record your observations in the table below. What do you think the relationship is? So, set it to 1 atmosphere, adjust the amplitude. What do we notice? So, I have audio enabled clicked here. I click the play button down here. I turn the frequency to somewhere in the middle, and we can play with amplitude. I have a high amplitude right now. What happens when I move the amplitude downward? So remember how we perceive amplitude. Amplitude is the height of a wave. As the waves get taller, as the pressure gets greater, the pressure difference in the wave, because sound waves are longitudinal, those pressure differences, we hear them better because our eardrums respond better. Remember when we looked at the 2 different kinds of waves in Lab 705, we looked at transverse waves. That's not a sound wave. Sound wave works by compressing air and then compressing and expanding air in a longitudinal wave. And remember, sound waves are waves that need a media to travel through. So if you go into outer space or you go into a vacuum where there's no air or water or something for the wave to travel through, it can't travel. So now let's see what happens when we start removing a media from the box. We're going to remove the air from the box and create a vacuum. And as the air pressure declines or decreases in the box, we're going to record the relative loudness of the sound at 5 different data points. And we'll look at the gauge in the simulation. We're going to make up our own scale for loudness. Normally you'd use decibels, but we don't have a decibel meter in our simulation, so we'll have to use our ears as our decibel meter. And we're looking for the relationship between the pressure in the box and the relative loudness. What happens when you take the air out of the box or take the medium away from the sound wave? So here's our simulation again. We're going to listen with varying air pressure, and I'm going to scoot this up so you can see the play controls here. My frequency is going to be right in the middle. I'm going to put my amplitude fairly loud. I'm going to hit play here. I'm going to make sure we're audio enabled so we can hear. And now I'm going to click Remove Air from Box. And as we watch this pressure go down, there's 1, 2, 3, 4, 5, 6, or 5 marks here. five areas between the marks. So it's about 0.2. It's going down 0.2 for every click here, for every mark. We're going to watch this and record this in the left-hand column of our data table on your lab sheet. And then you're going to listen and record the relative loudness for those 5 different points. So I'll start to remove the air from the box, and you'll know I'm removing air because the air pressure will go down. I don't hear anything now. We'll do it one more time so that you can listen very carefully now that you know what's going to happen, and make a scale based on how loud the sound is. I'll try a slightly different hertz because it's easier to hear. So I'll hit play. So when there's still air in the box, we're at 1 atmosphere. That's the pressure, that's the air pressure. You might have heard about atmospheres on the weather. We're going to start removing the air, and we'll see what happens to the relative loudness of the sound. Okay, you should have enough information to fill out your table. So now you should have enough information to fill out this table and explain what you think the relationship is between the pressure in the box, the air pressure, which we saw on that gauge to the left, upper left-hand corner, and the relative loudness, how loud the sound was. Now we're going to talk about the Doppler effect. You may have experienced the Doppler effect in real life. If you hear an ambulance go by, you kind of hear a higher pitch sound, and then it goes, as it goes by, it goes, the sound changes. Even though the ambulance isn't making a different sound, you hear it, you perceive it differently. And we'll explore why that happens. We're going to go to the simulation here and look at spaceships and what's happening there. There's lots of different animations on the internet about Doppler, the Doppler effect on sound. We're going to look at some of the light waves in space. We're going to use this simulation a little bit. The first thing we're going to do is hit the button called Observer Approaches, or this spaceship approaches. And we're going to watch what happens to the wavelength, how long it takes for one wave to go by, as this spaceship approaches a planet that's emitting light. So this is a light wave down here. So as the observer approaches, the wavelength gets smaller, and as it leaves the source, the waves gets much longer. Okay, now let's reset and see what happens if the source approaches. Let's see what happens if maybe you have a meteor coming at you that it's emitting light, or some kind of comet. Watch down here. You can see ahead of this, it's kind of pushing the waves closer together as perceived by the spaceship, and then they're getting further apart. And in space, that's called redshift and blue shift. We'll look at it again. If something is coming at us in the universe, it's shifting the light to be shorter wavelengths here, and that's towards the blue end of the spectrum. As it heads away from us in the universe, the wavelengths get longer, and that's towards the red end of the spectrum, so we call that redshift. Blue shift and red shift are all because of the Doppler effect, which also works on light waves as it does on sound waves. So now you should have enough information to answer the question, what happens when you press the button Observer Approaches and Source Approaches? What happens to those wavelengths as something is heading towards something else? And then what happens when it's heading away? What happens to the wavelength as you're departing? So now we have to see what happens when they both approach. What happens to the waves? Let's go look at that. So here's our simulation again, and this time we need to press both approach. Well, let's reset it here. And then let's have both approach. So it gets smaller, the wavelengths get smaller, and then they get much, much longer. Too far for accurate measurements. So as the two objects were approaching each other, the wavelengths got shorter. You can do it again on your own to check that out. Number 16, the waves in the simulation are representing light waves, and if observers saw light waves from a moving object coming towards them, so it's getting shorter, how would the light waves appear differently than if the object was stationary? Well, let's go look at the color spectrum quickly. So here's sort of a map of the color spectrum. You can see that the shorter wavelengths are blue and purple, and if the wavelengths get longer, if the light wave gets longer, it becomes redder. So if we see waves get shorter, the light is going to appear bluer. If something is heading away from us and the wavelengths are getting longer, the light, if we're seeing any from it, is going to look redder. So the phenomenon of wavelengths getting shorter is called blue shift, and the phenomenon of wavelengths getting longer as an object goes away from us, or we go away from an object, if we're emitting the light, is called redshift. Let's see if we were listening to a source of sound waves approaching us, what would happen to the pitch during the approach? So here's an example, just random example on YouTube of a car going by, and you can hear what's happening to the pitch of the sound as the car passes. You can hear the frequency of the waves as pitch, as how high or low the sound is perceived by your ears as the car is coming towards us and then as it's heading away. I'll play this for you. So now we've heard what it sounds, the Doppler effect sounds like. A source was approaching us, we heard a bit of a higher sound, and then as the car headed away, that car horn went, it got lower, it went, and then it went, as it went away. So you can think about what that means, how we hear the wavelength of the sound as it's approaching and as the source is departing from us. So we have been the observers. We were just observing something on YouTube, but we were listening to a source of sound move away from them. What happened to the car horn as it drove away from us? You probably have enough information to answer this question now. So if you need some more help with moving waves, the Doppler effect, you can watch this short movie. It might be helpful in studying for the test. The last part of the lab is the writing wrap-up. There's 10 words you need to use in a couple sentences or a paragraph. Make sure you don't skip this because it's worth 10 points. As you write your paragraph, you can either highlight each word or you can italicize it. Make sure that I know you've used each word by marking it somehow. You can underline it as well. Thanks so much. for paying attention to Lab 709. Good luck on your paragraph. Thanks so much. Bye-bye.